Thank you very much for the invitation to talk in this school. I would like to sort of give you an overview in the first part of this talk about several key concepts in machine learning which deal with representation of images. And then in the second part, I would like to talk a bit more about some of the applications we might really try to focus on in terms of using these representations for reconstruction, segmentation, and analysis of medical images. Okay, so let's get started. So what is the key challenge we're facing in imaging? So one of the key challenges we're facing is that our images are very high dimensional. So if even a 2D image might have 10,000 or more pixels or voxels. In 3D, of course, you end up with millions of these pixels or voxels. And we need to have methods which can actually deal with this amount of data. In many applications in machine learning, we're really interested in distance metrics. So if you train a classifier, of course, the distance metric is a key aspect which this classifier will use in some form, whether it's an SVM, random forest, another technique. So we really need to deal with these applications. And in many cases, what we're really trying to do is we're trying to find a low dimensional, or in some cases, we also call this a sparse representation of our data. And that's really what I'm going to talk about in the next 50 minutes, and then I'll show you some applications. So I'm going to start fairly gentle. Most of you will probably have heard of principal component analysis as a way of reducing dimensionality. But I thought it's actually quite an instructive example to go through and then see how we can generalize this to other types of approaches. And these other type of approaches are mostly nonlinear techniques. So PCA is really a linear technique. You can also view it as for example, as a linear autoencoder, if you're more familiar with concepts from deep learning. But of course, because PCA is inherently linear, I cannot really stack them together and build more complex representations because, of course, a combination of linear transformations still produces something which is linear. And then finally, I'm going to talk a bit more about dictionary learning and sparsity to round off the first part of the talk. So let's get started. I'm not going to stick to something very rigorous in terms of terminology and mathematics. I'm just going to use 3 different terms fairly loosely. I'm going to say manifold learning is roughly equivalent to dimensionality reduction and subspace learning. And as I said before, we'll focus in the first part here at the theory and then at the applications later on. I've also included in the slides, which I think you will all get towards the end, a number of references you can actually look up to find out more details about many of the things I'm going to talk about today. So let's start with an approximate definition of what a manifold is. A manifold you can loosely consider as having a very complex global structure, but if I purely focus on a manifold in a local, have a local view of a manifold, it pretty much looks to me like a Euclidean space. And that's quite important. So if you, for example, take the example of an ant or yourself walking on a surface of a large sphere or a torus, if you look locally, the world looks flat to you. And that means you see the world locally as being R2, but of course in reality you're on R2 embedded in R3. Another example of structures which we can view as manifold are, for example, 3D rotations. So 3D rotations I can effectively parameterize using 3 angles. But of course, if I look at the space of 3x3 matrices, these 3 manifold is embedded in a 9-dimensional space. And in a similar way, we can view images as occupying a hopefully low-dimensional manifold, but being embedded in a very large space of all the possible voxels. So here's a very simple example of what I really mean. So if you take this image, and if you take the pixel values, of course I can sort of view this in 2D as a matrix of pixel values, but I can also stack this together in a very long one-dimensional vector. And the key thing is, if I look at every image, it will be effectively a point in that very high-dimensional space. So the image you see here on the left-hand side is a cardiac MR image. Now, if I produce any possible vector here and look at this point in space, it's very unlikely that a randomly drawn combination of these values will actually look like a meaningful image to me, correct? Most of the time, for randomly produced here values, this doesn't really look like an image to me, or at least not like a cardiac MR. So actually, if I look at all the possible combinations which look to the human eye sensible as a cardiac MR image, you will actually discover that the space of these images is much lower, or the dimensionality of the space of these images is much lower than the dimensionality of this vector. And that's really what I'm trying to uncover. So the basic idea is I'm starting off with points in a very high dimensional space, living on a fairly complicated structure. So it can be, for example, a highly curved manifold. And I'm trying to uncover this mapping from this high-dimensional space to the low-dimensional space. And of course, the problem is that mapping is a priori unknown. I have to discover this. And I'm also going to hope that the dimension of the manifold, the dimension of this curved surface embedded in the high-dimensional space, is hopefully as low as possible. Okay? So we're really trying to find this low-dimensional representation. And an important thing is that we can have two different ways of thinking about representing our data. We can think about that we might have our original measurements, for example, the images themselves, as our vectors xj. Or alternatively, I might only have a set of measurements which correspond to distances or similarities between these different images. Okay? And in this case, I still can actually find a mapping from this high-dimensional space to the low-dimensional space. Okay. So, if you look in the literature, there are many reviews on this topic, and many of these different reviews have different ways of categorizing the data, these different techniques we're talking about. So, some say, well, there are linear techniques and nonlinear techniques. That's not very helpful in some sense because PCA is probably the only linear technique and all the other techniques you can view as nonlinear. Many techniques are spectral, and we're going to talk about a number of different spectral techniques. And they're spectral because they use the eigenvector analysis of a matrix to derive this mapping. Some of them are dense, and some of them are sparse. We're going to look at both of these approaches. However, the key thing, which I think is important to understand, that almost all of these techniques we're going to talk about, in some sense, you can view them as optimizing an objective function. PCA will be probably the most simplest objective function, but many of these techniques look at a convex energy function which they're trying to optimize. Some of the techniques we'll later on discover are not quite convex energy functions, but most of the techniques are actually convex energy functions. Okay, so I want to give you one very concrete example why it's so important to look at the manifold structure of your data before you, for example, apply your SVM or your other favorite classifier. So, of course, we want to reduce dimensionality of the data. That's always a good idea because we might, for example, want to visualize the data or cluster the data. but also the data might reside on a manifold which has a certain structure. And really the key thing here is if we measure distances along this structure, we need to have a meaningful representation of our distances. So what you see here on the left-hand side is a very famous data set called the Swiss roll. You can see this sort of a data set which is R2, but embedded in R3. So it's sort of a rolled up cloud of points here. Now what happens if I measure in the original space, for example, distances between this point and distances between these points here on my manifold? If I look at the Euclidean distance between these 2 points, you would actually say, well, the Euclidean distance is not very high, so these points probably should be classified together. However, if you really look at the geometry of the manifold, you discover that, truly speaking, there are no points in between these red points and the blue points. Actually, to get from a red point to the blue point, you need to travel all the way along the manifold. And this leads to a distance measure which we call a geodesic distance measure along the manifold. And that is a much more meaningful measure of looking at distances. So if I actually find a mapping which preserves this geodesic distance along this rolled up structure, and I can unroll this data set into 2D, I can actually measure in this low dimensional space distances which are an approximation of the geodesic distance via the Euclidean distance. And that's very important, correct? If I measure distance between the blue points here and the red points here, they're very far apart, like they should be. And that only really comes into play if you find the right manifold structure of the data. Okay. Good. So it's really very important to discover this, even if you don't really want to look at dimensionality reduction as your main objective, but if you simply want to actually find a representation of the data which really preserves the geometry of the space in which you're working in. Okay, so I'm going to go through some fairly basic notation in the beginning, and I'm going to go through over it quite quickly because I think most of you will be very familiar with it, and we have a lot of things to cover. So I'm going to basically view my images as vectors, x1, x2, and so on, and I'm going to stack all these images into a big matrix X, and I'm going to use that as my input representation. So X here is my input representation, and the output representation which I'm seeking to find are my yi's. So each xi will have a corresponding yi, but hopefully with a much lower dimension. So the other thing which is useful to very quickly sort of recap is what a basis means and how I can represent data in different bases. So if I assume that I have a canonical basis E, I'm going to say I have these basis vectors E1 to ED which span my space. And I can, for example, here use the unit vectors, and then I can represent any possible data item as a scalar combination of these of the data items together with the basis vectors. And I'm going to talk about a orthonormal basis if my basis vectors are both normal to each other, so they satisfy this criterion, but they're also going to be orthogonal to each other, so I'm going to have a proper representation which is orthogonal. Okay. So what happens if I change the basis of my data? So if I change the basis of my data with a new set of basis vectors, V, then I can simply write my change of basis as a matrix multiplication of my original data with my new basis vectors. Okay? And that's, you can really view this as a rotation of your coordinate space. And that's really a very useful starting point for perhaps the most simplest data dimensionality reduction technique, which is PCA. Okay? So just remember that if you're changing your basis, you're effectively rotating your coordinate system. Okay? So there are a few more things which are quite useful to keep in mind. So, for example, how does the variance of your data behave if you change the basis? So in order to look at this, I want to start with the assumption that all our data points are unit-centered. Okay? That simply means that your coordinate system, the origin of your coordinate system, is at the center of mass of all your data points, nothing else. Okay? And if your data doesn't satisfy this criterion, you can very easily compute the center of mass and simply subtract it from your data. Okay? If you have done this, you can compute your covariance matrix simply as x times x transposed. Okay? And the diagonal elements of the covariance matrix, I'm sure you all know, they represent the variance along the ith dimension, and the total variance I can simply calculate as a trace of that matrix. Okay? So what now happens if I change the basis of my coordinate system? What happens to the variance? Well, actually, there shouldn't really much be happening to the variance, because if you think about this as a rotation, you can probably guess what should happen to the variance after a rotation. So if you take your new representation y as this matrix multiplication of your data with your new basis vectors, then obviously you find out that the new data set is still zero-centered, because I'm just doing a rotation. But I can also express the covariance matrix in this particular form here, which is going to be quite useful. Actually, the reason for how you actually derive this form of the covariance matrix, you can just write it down like this here. But most importantly, if I look at the total variance in my basis, actually discover I haven't really changed that variance, because if I compute the trace of my original matrix and the trace of my new representation, then it's still the same. Okay? So I'm still ending up with the same variance if I simply change my basis. Okay? So now let's actually start applying this idea to PCA. So PCA, I'm going to give you a fairly unmathematical explanation, an intuitive explanation of how you can think about PCA. There are many different ways how you motivate and derive PCA, but I'm just going to use a fairly informal representation. Okay? So I'm going to start off my high-dimensional data points, and I'm going to use a linear projection as a way of reducing dimensionality in the data. Okay? And I'm going to use an objective function which is based on the variance of the data. So I'm going to try to represent the dimensionality reduction as a linear projection of the data onto a lower dimensional hyperplane, and in such a way that I preserve as much variance of the data as I can possibly do. So in some sense, you can view this plane as a subspace of the original data, but you can also interpret that plane as a manifold, and therefore you can sort of view PCA as an instance of manifold learning techniques. Okay? Good. So how do I now proceed? I've said I want to calculate a projection which tries to preserve as much as possible the variance of the data. So I'm trying to find a new set of basis vectors, V1 to Vd, and with a restriction that the small d is much smaller than our capital D. And one way of proceeding would be to simply say, well, why don't I take my first direction as the direction of the maximum variance, okay? And that's a fairly intuitive interpretation, because if I look in the direction of maximum variance and I project onto that, I'm going to preserve quite a lot of the variance, okay? So I now simply select the initial vector as the direction of maximum variance. I remove that from the data components because I've explained it now with V1. I'm going to now keep on doing the same thing with V2 and so on until I've actually reduced the dimensionality as much as I wanted it to do that. So in every step, I'm computing the direction of maximum variance in my updated data, and I remove that variance because I've now explained it. And these set of basis vectors you end up with are called the principal components of your data. Okay? So you can write this more formally down. It's fairly easy to actually do this, and you can sort of come up with an iterative algorithm if you wanted to do that. And you stop if you have explained enough of the variance in the data. 90%, 95%, really that depends on what you want to do. Of course, that's a sort of iterative algorithm which nobody really would use in practice to look at PCA and actually performing this. We can also solve the same problem by doing eigendecomposition of the data we have, okay? And that's why PCA is called a spectral method, because it looks at an eigendecomposition of your covariance matrix C. Okay? So we can compute the eigenvectors and the eigenvalues of our covariance matrix relatively easily because the covariance matrix, of course, is real and symmetric, positive semi-definite. So it's quite easy to compute eigenvectors of this matrix. Okay? And what I can actually do, I can also look at the eigenvectors and the eigenvalues, and I can sort them. And if I sort them according to decreasing eigenvalues, I discover that the principal components V1 to Vd correspond to the first d eigenvectors, so the eigenvectors which have the largest value. Okay? So here's a simple example of what happens if you apply PCA to a very simple data set. Okay? I'm going from something which is really simple, a 3D point cloud, but you can see that the 3D point cloud has a certain direction in which has maximum variance, and I'm reducing it from 3D to 2D. So not a massive dimensionality reduction, but you can see that the PCA has preserved one of the directions in your new coordinate system, namely that of the first principal component, is the direction which has most of the variance of the data. Okay? Okay, so there are a couple of tricks you might actually apply to the calculation of PCA if you want to do this efficiently for higher dimensional data. Because if you really think about what I've done, if I compute eigenvectors and eigenvalues of a covariance matrix, then you very quickly discover that this approach has a fundamental limitation. If I have a data set of 100 images, but every image has 1 million pixels, well, strictly speaking, I would need to compute a covariance matrix which is 1 million by 1 million. Clearly, that's not feasible. Okay? So if our original dimensionality of the space is very large, I immediately end up with a problem. Okay? So it's not really feasible to do this. However, there's a saving grace which we usually have in imaging. So in many cases, if I ask you how many data sets you have, well, you might say, well, I have 100 images or 1,000 images. And if you have 1,000 images, you already talk about big data, right? But each of these data sets has 1 million voxels. We can do a very simple trick, and instead of calculating the eigenvectors of the covariance matrix, I can compute the eigenvectors of another matrix, G, and I can actually use this to compute the solution to my problem. So G, so remember that the covariance matrix is X times X transposed, okay? My new matrix, which I'm going to analyze, is x transposed times x. So I'm just swapping the order in which I do multiply my matrices. However, that has, of course, a significant effect on the size of G. It's going to be now a much smaller matrix. If I have 1,000 images, I end up with a matrix which is 1,000 by 1,000. Okay? So that's very, very simple. However, it turns out that if I want to compute the eigenvalues and eigenvectors of my original matrix, covariance matrix, I can compute this directly from G. So for example, lambda, an eigenvalue of this big matrix, is going to be also an eigenvector of my matrix G. Okay? So this matrix is called the Gram matrix, and I'm not going to really go into very much detail, but it's probably really sufficient to say that the Gram matrix and the covariance matrix have very different dimensionalities, but the eigenvectors of the two matrices are closely related, and the eigenvalues turn out to be the same. So with this very simple trick, which is really well known, we can compute now PCA of a very, very large data set. Okay? If I give you lots of images with millions of voxels, you still can do this dimensionality reduction. Okay? So now you say, okay, we're all done, can reduce dimensionality, can all go home. Well, let's take the example I showed you before, this Swiss roll, and apply PCA to it. Turns out, actually, it produces not a very good solution. And it's fairly obvious why it does this. Remember that PCA is a linear technique. I have a structure, which is a manifold, which clearly has a complex shape, so it's not a flat space. Therefore, if I do a linear projection onto a plane, I'm not going to end up with any sensible result, no matter how I choose my plane. Okay? So clearly, PCA is quite powerful, but even with a simple example like this, it doesn't produce a very good answer. So let's look at the first sort of nonlinear dimensionality reduction technique, or manifold learning technique. It's called IsoMap. So IsoMap is probably 20 years old, so it's a well-known technique. And instead of using the covariance matrix to analyze your data or your manifold, it actually works on the space of pairwise distances. So I'm going to assume that I have a matrix delta, which contains my pairwise distances between my data points. And I'm going to analyze that particular matrix rather than analyzing the covariance matrix. Okay? So if you have your original data points, you can, of course, compute distances very simple by calculating your Euclidean distance. But remember that the measurements in the original domain might not be very good approximations of my distances. So if I, for example, have this highly curved structure, then the Euclidean distance between A and B is going to underestimate the geodesic distance between A and B. And that's something which I would like to avoid. How do I avoid this in IsoMap? Well, it's a very simple idea. So let's take a slightly different view of the data. All my data items now become vertices, which unfortunately you can't see very clearly in this picture. But all my data items become vertices, and the edges between the vertices are the pairwise distances between these vertices. Okay? So I'm going to have a graph with vertices and weighted edges. Okay? Now, I told you before that the distances are not very reliable if I measure, for example, the distance between this vertex and this vertex here, because they're far apart. And the Euclidean distance might not be a good approximation. Can any of you think what I can actually do to this graph to try to solve that problem, that my distances might not be very reliable? Anybody got an idea? I could. do? You can also answer in the first row if you... Take out some edges, exactly. So I can take out some edges, and probably what I should really do is take out the edges which are the long distance edges, and I'm just going to keep the edges to the nearest neighbors, okay, because these are small distances. So I'm going to sparsify my graph by just keeping, for example, those edges which are below a certain distance, or I'm just going to keep the k nearest edges. I can basically use both approaches. Doesn't really matter. Of course, I have to take care that I don't disconnect my graph, because if I disconnect my graph, I can no longer reach every vertex from every other vertex. Okay, so now I've removed some edges. Can you think of what that might actually, why I want to do this? Why would I want to do this, and what should I do next? So now I have a sparse distance matrix, correct? I no longer have a full distance matrix. I have now a sparse distance matrix. What could I do in order to go back to a full distance matrix? Going back to a full distance matrix means I still want to have a distance from this point to this point. So the most obvious thing you can now do is you can find the shortest path in this graph, correct? If I still want to go from here to here, I can find the shortest path along the edges in the graph. And remember that the edges are all weighted, so finding the shortest path is a relatively straightforward, simple calculation, and is going to give me an approximation of my geodesic distance between the points. Okay? So I'm just going to show you sort of a very simple example of why this works. So let's just imagine we have, again, this Swiss roll example. Okay? So I have my data points here. You can sort of see that they form this nonlinear rolled up structure. And really the question is, how do I find the distance between this point and this point here? So if I view this as a graph, I can connect as my sparse graph. I can sort of connect points which are nearby. If I do this, you can see that I'm not going to end up with a fully connected graph. So obvious solution would be to say, actually, let me use a higher threshold or more nearest neighbors. If I overdo this, I clearly end up with a bad solution as well, correct? Because now, if I want to go from here to here, I no longer have to go the geodesic path. I can simply take a shortcut, and my distances are not going to be very meaningful. However, if I choose my distance threshold in the right way, then I end up with a good way of approximating my distances, because in order to get from here to here, I have to find the shortest path, and that would take me along the manifold structure of my data. Okay? So you can sort of see that this is going to be a good approximation of the geodesic distance if and only if you choose your threshold for sparsifying a graph in the right way. Okay? And that's a quite important step. Okay? So let me sort of now walk you very quickly through the basic algorithm how to compute this. So let's take our data features. If we start off with the original data points, compute the pairwise distances. You might skip this if you already have that pairwise distance matrix. I'm going to choose an edge constraint. As I said before, I can either remove all edges which are above a threshold epsilon, or I can opt for keeping the k nearest neighbors. Then I'm going to estimate all the distances which I've removed by estimating the geodesic distances as the shortest path in my data set. Okay? And then I'm going to apply an algorithm which we haven't quite discussed yet, and I don't think I'll have time today to really go through this particular algorithm, but I'm going to analyze the matrix D using something called classical scaling, which basically is a spectral analysis of my distance matrix. I have some slides on this, so if you get the slides later on, you will be able to read a bit more about classical scaling, but I'm going to skip this because I don't think we have enough time to do this. Now, obviously, this is going to be very difficult for a large matrix, but remember that here, the matrix which I'm computing is a distance matrix between my data items. So the n here is going to depend on how many images I have, not on the size of every individual image in my data set. Okay? Good, so we've done this. So the result of IsoMap applying this to this very simple, trivial data set going from 2D to 1D is simply color-coded here. So the coordinates of every data point are represented by their color in the reduced mapping. You see all these blue points are grouped together, and the red points are quite far apart from the blue points in my new coordinate system. Okay? So let's take another look at a different algorithm, which is called Laplacian Eigenmaps. And the key difference here is I'm not going to make the assumption that I know distance, the distance matrix of my data. I'm going to make the assumption that I know the similarity of the data items, but not the distances. And that's an important differentiation because distances are, of course, produce a metric space. Similarities don't really have such strong requirements for actually, or don't impose such strong requirements for my data. So I'm going to start off with a new matrix called W, which the entries in that matrix represent my similarity. And that similarity could be whatever you choose your similarity to be. It could be, for example, similarity of features you have extracted from the image. Cis features, whatever features you might have. Could be, for example, sums of square differences between the images, any other possible measure you want to have. If you have actually a distance measure to start off with, then you can easily convert your distance measure into a similarity by simply computing the exponential of your distance and choosing a parameter t which controls the size of your Gaussian kernel, which effectively smooths your distance measures while converting them into a similarity measure. Before we go into the Laplacian eigenmaps in detail, I just want to show you a few examples of what you can use as similarity measure. Okay? So I think Sandy has probably talked a bit about image registration before. And in image registration, there are a couple of different similarities measures you can use. I can use, for example, the sums of squared differences. So that's, for example, the similarity of two images. I can use the normalized cross-correlation between my two images, or I can use, for example, the mutual information of the two images. All of these measures produce a similarity between my two images, and I can use this similarity to drive my Laplacian eigenmaps calculation. However, if you're a bit more familiar with image registration, then you know also that I can use derived features from the image registration to explain the similarity of my images. So if we assume that we have a mapping from one image to the other image, I can, for example, look at the first derivative of my mapping or the second derivative of my mapping to measure how much I had to change the shape of one image to match the shape of the second image. So if you so will, these features are, for example, very simple features which measure the similarity of your image in terms of appearance. And these features, which are computed from the deformation of one image into the other image, are much more related to the shape of the images. Okay? So if you really care about the shape, you should perhaps think about using something which you can derive after an image registration. Otherwise, you can use an appearance-based feature. So Laplacian Eigenmaps uses a very similar representation to what we had before in IsoMap. It's also going to use a graph representation. So all my data points, my images are vertices. I have weighted edges. And the key difference to IsoMap is I'm only going to produce a sparsely connected graph, and I'm not going to actually transform that sparsely connected graph back into a fully connected graph. I'm just going to work with my sparse graph. Actually turns out that that's actually a quite efficient way of analyzing your data as well. So I'm going to end up with this sparse matrix, and I'm going to analyze this sparse matrix in a spectral fashion. But I can also write down what my objective function is, which I'm going to try to optimize. I'm going to say I would like to find a new coordinate mapping y, which minimizes this objective function. If you look a bit more closely at this objective function, it becomes fairly easy to see what this does. So what does this do? Well, if I'm going to have two data items which have a high weight means they have a high similarity. I would like to place these points close together in my new mapping. Okay? So I'm basically going to force 2 points, yi and yj, to end up in the same location in the manifold, or close enough location in the manifold if wij is also high. Okay? And if I have a very low similarity, if wij is nearly 0, then I say, actually, I don't really care how far my points are apart, because they're not very similar, correct? And that's exactly what you want your mapping to do. So we can optimize this mapping, again, through a spectral analysis of the matrix W. But of course, I need to take a bit more care to do this properly, because minimizing this expression can also lead to unwanted solutions. So one obvious solution is I'm going to map everything to the same point, correct? If I map everything to the same point, I'm going to minimize this function. We're going to have a similar objective value of 0. Can't get any lower than this. So I need to actually also make sure that I rule out these unfeasible solutions or undesired solutions. And I can do this by adding a few constraints which, for example, preserve or prevent mapping everything to 0. So how do I actually optimize this mapping? Is I compute something called the graph Laplacian, which is this matrix L, which is a diagonal matrix or the degree matrix minus the weight matrix I've derived. And the degree matrix is simply a matrix which tells you which of your data items are likely to be outliers. Because what happens if you have a very low degree, that means you have very low similarity of a data item to all other data items. So if this entry dii here is very low, then your data point is going to be likely an outlier. And if you do a bit of math, you can show that you can optimize this criterion by optimizing or calculating the trace of this matrix here of the graph Laplacian. Okay? So again, it's fairly simple what you can actually do in practice to calculate this. Okay? So we need to take a bit more care about avoiding these collapsing solutions, but probably don't really need to discuss this in much detail. So at the end of the day, you compute eigenvectors of this matrix L, the graph Laplacian, and we have to discard the first eigenvector because that's a sort of trivial solution, and then we can take the other eigenvectors as the coordinates in our new mapping. So here's an example of what happens if you apply Laplacian Eigenmaps to these, to the Swiss roll example, and you can see that it actually does a fairly reasonable job at preserving distances between points which should be nearby. So you get them mapped into the right coordinate system. Good. So here a few more, actually I can probably skip this about the generalized Laplacian because we probably don't have enough time to go through this. So I want to go through two more manifold learning techniques which are quite related, and then spend the last 5 minutes talking a bit more about dictionary learning. So another technique which you can apply to your data is called local linear embedding. And the idea here is very intuitive. It says actually if I look at my data in a local neighborhood, then in a local neighborhood the space is flat, and I can make the approximation that Euclidean geometry is perfectly adequate for describing my data. And so LLE exploits exactly that idea by trying to approximate every data item using its nearest neighbors. Okay? So what do? You choose your nearest, the number of nearest neighbors for your data item, and then you find the best linear approximation of each data item through a weighted combination of your neighbors. Okay? And if you're in a linear space, that of course works perfectly sensible. And remember that I'm only using my nearest neighbors. So I'm not going to use points which are far apart. I'm just going to look at my nearest neighbors. And I'm going to represent every data item using this weighted combination of my, my high-dimensional points. Okay? And the real idea is that these distances, or these weights, which I have computed in my high-dimensional space, they should be still meaningful weights in my low-dimensional space after dimensionality reduction. Okay? So if you write down the objective function for local linear embedding, it's basically saying, okay, I'm going to minimize the distance between the data point I have and the weighted combination of the other data of its neighbors, which try to represent that data point. Okay? And by getting them close together, you actually minimize this energy function, and you find a good approximation in your lower dimensional space. So again, turns out you can do all this optimization in a fairly efficient way using a spectral analysis. Now this time the spectral analysis is a spectral analysis of this matrix here. And again, if you look at the eigenvectors, they will tell you your new coordinates in your lower dimensional mapping. Okay? So it turns out that actually this is also very closely related to Laplacian Eigenmaps. Again, probably going to skip this, but the idea is fairly similar to what you're actually doing in Laplacian Eigenmaps. So the last manifold learning technique I want to briefly cover is something called T-distributed stochastic neighbor embedding, and it's perhaps a manifold learning technique which, if you look at the literature, has been mostly proposed for visualization of data. And the idea here is, instead of working with similarities or distances, we work with a more probabilistic point of view. So I'm going to represent, instead of using similarities, I'm going to express everything in terms of probabilities between which tell me how the joint distribution of points in the high-dimensional and low-dimensional mapping behaves. Okay? So I'm going to define these joint probabilities in the low-dimensional mapping, which I'm going to express in this form here. This is what the original stochastic neighbor embedding proposed by Hinton in 2003 used. So this is obviously sort of a Gaussian model for your probability distribution. And the stochastic, the T-stochastic embedding technique by van der Marten and Hinton uses a slightly different form of this probability distribution, uses a Cauchy distribution rather than a Gaussian distribution, which has certain advantages in terms of preventing points of bunching up too much in your new embedded space. And the energy function you then optimize is the error between your input similarities, Pij, and your output similarities or probabilities, Qij. And because they are probabilities, you can use, for example, the KL divergence to measure the difference between the distributions P and Q by simply optimizing this cost function. Now, it turns out that this is no longer a spectral approach. Actually, the cost function is non-convex, and therefore I typically need to use some stochastic gradient descent algorithm to find the optimal solution for this problem. So I want to show you a final example of how these different techniques compare. So this is a data set, images from a database called MNIST, which contains effectively numbers, handwritten digits. And each handwritten digit between 1 and 10 is color-coded here. And you can see that this T, S, and E leads to almost sort of a clustering of the data, whereas the IsoMap and the local linear embedding end up with a much smoother manifold. But of course, this manifold might be more useful, for example, for a visualization and a sort of analysis of the data. Good. I have a few more slides here on large-scale manifold learning. You can have a look at them, which just show you a bit more how you scale this up to very large data sets. For example, if you have 18 million images, obviously computing similarities is no longer feasible. Finding nearest neighbors becomes very hard. So I'm going to skip this, but this paper contains a very good overview of how you get around some of the numerical problems you have when you have to construct these huge graphs. Okay. So the final thing I want to talk about briefly about is something which is a slightly different view about dimensionality reduction. So at the moment, we have always talked about image level representations. That means I'm taking the whole image. Unfortunately, you can't see this very well. This is a brain, this is a heart, and this is a fetus. And compressing that into a low-dimensional representation. Now, that might not be the best possible thing to do. I can also at patch levels. That means I'm going to take small patches from the image, and I'm going to try to work out how I can compress these small patches in the images, and I'm going to use a local representation rather than a global representation. And the idea here is I can represent all these patches, which I have, using a dictionary D, which you can sort of view as every column in this matrix D here as a dictionary item. It's effectively a small patch of my data. And I'm going to reconstruct my original patch using a sparse combination of these dictionary items. Okay? So this vector alpha here is going to be sparse, so it has very few non-zero entries. If I'll multiply this vector with my dictionary, I'm going to recover the patch which I'm trying to model in my image. Okay? And then I can, for example, piece together my image using lots of overlapping patches. What could I choose as a dictionary? So how do I choose effectively this matrix D? Well, there are many different ways, correct? One obvious approach is to simply use a fixed basis, for example, a DCT, a cosine transform, or a wavelet basis, and I'm just going to use that as a fixed basis. But another alternative is to learn the basis, the optimal basis, directly from the data which you have. Okay? And in this case, I want to choose a dictionary which gives me the sparsest possible reconstruction of my signal. Okay? So I want to minimize this difference over all possible dictionary possible dictionaries. And if I do this, I can use, for example, one very well-known algorithm called KSVD, where I formulate the problem of recovering the dictionary and the sparse coefficients as a joint problem. So I'm trying to estimate D as well as A, the sparse combination of the dictionary atoms, by minimizing over the solutions D and A. And this is called the KSVD algorithm, which is a fairly powerful technique for learning both these dictionary elements as well as the sparse coefficients in this dictionary elements. If I do this, I can then start recovering my entire image using this sparse combination of dictionary atoms. And the dictionary atoms are, of course, fixed for all the images I have. Okay? So these are generic for a whole class, and then the coefficients are going to be specific to your image which you're trying to recover. Okay? So just want to show you an example and finish the first part with this example here. If I take, for example, this natural image, I can reconstruct this natural image patch by patch through a sparse combination of these dictionary atoms. And I can do the same thing, of course, with a medical image. Okay? You see that these dictionary atoms are different for medical images than they are for natural images. And this is something quite powerful because that means that these dictionaries can be class-specific. Okay? Because you can optimize them for a given class of images, for example, natural images or medical images. Okay? So I have a few more slides with reading material, but you can have a look at those in a moment. And I think we probably should stop here and take a break for 10 minutes or so, 5 minutes. And then in the second part, focus a bit more on applications of manifold learning and dictionary learning. Good. Thanks.